with 9.1, which is called scale factor. And I'm going to start with what might be a little bit of a review for some of you, but it might also be brand new. And that's okay, whichever of those two it is for you. Not a big deal because I'm going to build in review anyhow. So for people who haven't done this before, you'll learn it now. So basically we're looking at a series of different types of triangles. Can you show me with your hands how many of you learned these triangles, the different types last year or at some point? Okay, good. So it's kind of review for a lot of people. It's up to you. You don't have to write it down, but I'm going to just zoom in to show you some of these. The first one that we're looking at is a right triangle. What degree has to be there in a right triangle? 90 degrees. So that's the little black box in the corner. You need to have that in order for it to be a right angle triangle. And remember, what formula do we usually deal with a right angle triangle? Pythagorean theorem. Good. The next one is scalene. So this one right here. Anybody know, could you describe what scalene means? Or what do we know about scalene triangles? Anybody know anything about them? Yeah, Tracy? Thank you. All the sides are different, right? Everybody knows that? So that's our scalene triangle. That's the property of it. Equilateral, I feel like the name kind of says it all, but what do we know about equilaterals? Helena? All the sides are the same. What else is all the same? All the angles are also the same. So that's the deal with an equilateral, and I feel like this is true of so many things. A lot of times the name kind of gives you hints as to what it is. And then the last one is an isosceles. Do you know isosceles? Or who can tell me about an isosceles? Richard? Yeah, two sides have the same length. Does anything else end up being the same in this as well? There's one other, the two angles. So see this angle down here and this angle down here? Those would also be the same if the two sides are the same. So far, so good? Feels like review? Good? Okay, so that's the first introduction to this. And then, so that's the triangle family. Now we're on to the quadrilateral family. I don't know how familiar you are with these, but that's okay. We're going to go through them. So maybe let's start up here with just where it says general quadrilateral. How many sides in a quadrilateral? 4 sides, right? So 1, 2, 3, 4. Then it points down here to a kite. We don't really need that, but it's there, so it's fine. Do you know when we get down here to a rhombus? What's a rhombus? What are the properties of a rhombus? It's a sideways diagonal? Diamond, yes. What are there properties about the sides that we know about? Like if we look at this side and this side, what do we know about them? They're equal and they're parallel. Everybody know what I mean by parallel? Exactly the same distance apart if we were to measure them. Okay, so those are parallel, and these two opposite sides are also parallel to each other. Can you see that? So it's like we took a regular rectangle and we just sort of smushed it at the top so that the sides ended up slanted. Does that make sense? And then when we look down here, a square, we all know that, right? All these sides are exactly the same. The angles would all be 90 degrees. Squares we're familiar with, no big deal. And then up here we have the parallelogram. Well, what's the difference between a rhombus and a parallelogram? Maybe that's the only thing we need to talk about here. Those are parallel, those are parallel. So why would a rhombus and a parallelogram? In a parallelogram, right? Good. In a parallelogram, the two opposite sides can be different lengths. So the two top and bottom ones, we can see in this one, it's quite a bit longer. The side ones are quite a bit shorter. But in a rhombus, they're the same. Does that make sense? So I should correct myself. A rhombus is if we took a square and squished it top and bottom. Like we just squished it so that the sides end up getting slanted. And a parallelogram is if we took a rectangle and we squished that top. Maybe not squished. You get what I'm saying, right? We flatten it top and bottom so the sides end up slanted. And then a regular rectangle, who needs to talk about that? Isn't that old news? We all know that inside out. How about an isosceles trapezoid? I don't know, this isn't super common, but what do you think it is based on the name? Well, first of all, let's go up here first. What's the trapezoid? Richard? Yeah. Yeah, so these two are parallel to each other, but notice that they're different lengths. And then the two opposite sides are not parallel, they're actually going in opposite angles. Does that make sense? And then isosceles trapezoid would be, well, what's an isosceles triangle again? Two equal sides and two equal angles. So do you see that those would be the same, it's saying, and those would be the same length if we were to measure them? They're just not parallel to each other, but they are the same length and form and create the same angles. Good? So there's a little bit of just background information, which we often do when we're starting off a new section. And then there's this side angle side. Have you heard of this side angle side? When we are dealing with two similar triangles. These two triangles are called similar triangles. Notice they're not the similar size. One is like this one's much bigger and this one is smaller. So what is similar about them is that they have a side angle and a side that are similar. So I'll show you what I mean by that. Although they are different sizes, see this angle here? It's the same measurement as this angle here. And there's a relationship between the length of the side at the bottom and the length of the side here. If you look at it, if this is 6 and 10 and this is 3 and 5, what's the relationship? What is the small one compared to the larger one? Kira? Good, it's basically half of the length, right? So if we knew this side here, I could just take it and divide it by 2 to figure out this side here. So we are in similar triangles. If we know there's a side angle side relationship between them, we can use that to come up with the measurements of the missing sides. So these are just properties of quadrilaterals and triangles that we'll be using to sort of calculate and find measurements for. Are we good so far? And are there questions so far? So notice here it says 6 over 3 equals 10 over 5. So that's showing that relationship, because if I divide this out, what is 6 over 2? 6 over 3, what does that equal? Just told you the answer. It's 2. And what's 10 over 5? 2. So do you see, although they're different lengths, the ratio is the same. They end up being 2 equals 2 if we were to reduce those fractions. So far, so good? Okay. Let's take a look at an example of how this comes up. On the left here, we have a real horse and we're told the measurements. So I'm going to read it to you because I don't know if it's super clear for you, but the real horse is, it says 1,500 millimeters high. First of all, let me ask you this. Would you measure a horse in millimeters? Probably not, right? Like, how big are millimeters? We all know how big millimeters are, right? They're tiny. So why do you think that we've that they have used millimeters in order to look at this measurement. Well, actually, remember how we looked at misleading graphs and all of that stuff? So that's a good point there. It could be to exaggerate to make it appear much bigger than it is. But notice on the right-hand side, we also have this drawn horse. So we're looking at an image versus the actual object. This is the actual object, the real-life horse. And on the right here, we have the drawn horse or the image. The image, does it make sense to measure it in millimeters? So it's like a little diagram on a picture, and that is 150 millimeters high and 200 millimeters long. So the reason that they've given the measurements for the real horse in millimeters is so that we can make that comparison. If we are going to make the comparison between the real and the image, looking at scale factor, so looking at this thing down here, in order to do that, we need the same units, which is millimeters in this case. So that's the first thing. If it's given to you in different units, your first job is to convert it to the same units. Good? Okay, so to get the scale factor of what this would be, we have a formula. So you need to know this formula here. Image length, so the drawing, over the object length, which is the actual size. So in this scenario, what is the image length? It doesn't really matter which one we choose. We could use, see how they're telling you the height versus the width of what it would be? So it doesn't matter which one we use. We just need to keep it consistent for the two of them. So do you see that if I'm going to use 150 millimeters, then I'm going to use the 1500 millimeters for the actual size. Does that make sense? So to get the scale factor, what value goes at the top here? The drawing, so that would be 150 millimeters, over the object or the actual size, so that's going to be this 1500 millimeters. So when we go to look at this, well, you could just, do you see that we can cancel those out? The units would be gone because we're looking at scale factor, but what do we end up getting? Can we simplify this? 15 over 150. What is that the same thing as when we simplify it? Well, does 15 go into 15? Yep, so we get a 1. And how many times does 15 go into 150? 10. So we could give this scale factor as 1 over 10. Or what is that the same thing as a decimal? Yeah, this is also the same thing as 0.1. Good?
That was easy.
Good? And that's your assignment for right now. I'm going to stop you in a little